Good evening, everyone. Welcome back to our day 4 on FDP. So today we are going to discuss a new topic. So we'll quickly recap what we have covered in the previous session, and then we'll start with the topic. In the last class, we have understood a project management methodology called CRISP-MLQ. Right? What exactly is CRISP-MLQ? CRISP-MLQ stands for Cross-Industry Standard Process for Machine Learning with Quality Assurance. And this CRISP-MLQ is being implemented for achieving any of the tasks. Okay. In order to build an AI application, we use a methodology and it is CRISP-MLQ. How many phases do we have under CRISP-MLQ? There are in total 6 phases. What are the 6 different phases we have under CRISP-MLQ? Business and data understanding, data preparation, model building, model evaluation, model deployment, and monitoring and maintenance. Right? So, as part of phase 2, we are going to prepare the data. The data will be prepared for the next phase. Right? The data will be prepared for the next phase. It is model building. So, as part of data preparation, we have 3 subphases. What are they? They are EDA, data cleaning, or also called as data pre-processing, and feature engineering. So, in the last class, we have understood what exactly is EDA, Exploratory Data Analysis. Am I right? So, what do we have under EDA, guys? Under EDA, there are in total 4 moments. First moment, second moment, third moment, and fourth moment. And we also perform graphical representation. That is nothing but we visualize the data. So when we perform all these movements, first movement, second movement, third movement, and fourth movement, we get insights. From the raw data, we get insights. Apart from calculating the measures, we also visualize the data, in which we have univariate plots and bivariate plot. Right? So what is the purpose of first movement, guys? What is the purpose of first movement? What exactly we get from first movement? Business decision. First movement business decision will capture the representative value or the center value. The center value or the representative value will be captured by first movement business decision. And what are the measures do we have under first movement? We have mean, median, and mode. Mean is nothing but average. Mean has a disadvantage. It gets influenced by outliers, the extreme values. And for that, we have median measure. Median represents the middlemost value of an ordered data set. Right? Then, median does not get influenced by outliers. Third measure is mode, which represents the most repeated value. The most repeated value within the data set will be written by mode measure. And mode also gives the information about clusters, groups, segments. Okay, within the data, if you have any groups or any clusters, we'll get the information by mode calculation. Yes. Now, next to first moment, we understood second moment. Second moment captures what? Second moment captures the measure of deviation from the center. Okay, how the values, the rest of the values are deviated, spread. Whether there is a dispersion in the data or not, we'll understand by the measures of second moment. And under second moment, we have measures like variance, standard deviation, and range. And range. When it comes to variance, variance has a disadvantage. It does not return the actual spread. It returns the squared spread. So in order to return the actual spread, we use standard deviation measure, sigma. Then finally range. Range will return us the difference between the maximum and the minimum value within the data. That is what range is going to return us. Coming to the third moment. Under third moment, we have this third moment is capturing the measure of asymmetry. So it actually captures the direction of spread from the center. The direction is being captured. Either we have a long tail towards the left hand side, or do we have the long tail towards right hand side? Is what we are trying to understand from the measure of third moment. What is the measure under third moment? It is skewness. And this skewness is of three types: positive skewed, negative skewed, and no skewed data. Right. So when it comes to positive skewed data, we'll have the wrong tail towards right hand side. So that means the extreme values will be part of the right hand side. Then coming to the negative skewed data, we'll have the long tail towards left hand side. The extreme values, the outliers will be part of the left hand side. They are towards our left hand side. And if it is no skewed data, we'll have a z distributed curve. A normal distribution curve is what we observe. If there is no skewness, that means you'll exactly find a bell-shaped curve where mean, median, mode will exactly lie at the center. Right. Then next to third moment, we discussed fourth moment. Under fourth moment, what exactly fourth moment is capturing? Fourth moment captures measure of peakedness. It is capturing the peakedness. Either we have a tall peak, a sharp peak, or whether we observe a wide peak is what fourth moment tries to capture. And the measure under the fourth moment is called kurtosis. It is called kurtosis. Kurtosis is also three types: positive kurtosis, negative kurtosis, and no kurtosis. Okay. So when we say positive kurtosis, that means we get a tall peak, a sharp peak with long tails. When I say negative kurtosis, you'll observe a wide peak. Instead of data being concentrated at one single point, the data gets spread. Right. So these are the points that we have discussed coming to moments, 4 moments. Next 2 moments, we understood visualizations, in which we understood univariate visualizations and bivariate visualizations. Both. Univariate means we'll work on one column at a time. Bivariate means we'll try to visualize data of 2 columns. Under univariate, we understood bar plot, histogram, box plot. And we also understood QQ plot. But under bivariate, we understood only one plot. It is scatter plot. So coming from the univariate analysis, univariate visualizations, histogram. What is the purpose of visualizing histogram? Histogram gives the information about data distribution. It gives the information about data distribution. Okay, whether the data is skewed. Okay, we'll get the entire information when we visualize a histogram. What about box plot, guys? What is the purpose of visualizing a box plot? The purpose of visualizing box plot is box plot is the only visualization which gives the information about the presence of outliers. Whether the outliers are present or not, we'll get the information only when we visualize box plot. Right? And box plot uses the formulas. What are those formulas? Q plus or minus 1.5 times of IQR. What is IQR? IQR is nothing but interquartile range, which is nothing but the difference between Q3 and Q1. Q3 minus Q1 will result as IQR. Then, next to box plot, we understood QQ plot. What is this QQ plot? QQ plot is actually representing quantile plot. It represents quantile plot. On x-axis, we take theoretical quantiles, nothing but z values. On y-axis, we take sample quantiles, nothing but our data. Our data will be on y-axis, and on x-axis, we take theoretical quantiles, nothing but z values. And we'll observe, if we observe the scatter, passing through this line, then we see the data is normally distributed. The data is normally distributed. What if the scatter, if the majority of the points is not passing through the line, then we see that the data is non-normally distributed. So today we'll visualize scatter plot, guys. Sorry, my bad. QQ plot. Today we'll visualize QQ plot. Then next to QQ plot, we understood scatter plot and also the bivariate plot. What is the purpose of visualizing scatter plot? Scatter plot will give us the information, it explains the relationship. It explains the relationship between two variables. Okay, if you take two columns and if you want to get the relation between these two columns, whether they are correlated or uncorrelated, you'll get the information when we visualize a scatter plot. Scatter plot gives us three main things. One is the direction, the second one is about linearity, and the third one is strength. Right? Yes. But strength is subjective in nature. So that is why, our statisticians have come up with a measure called correlation coefficient, which is represented with small r. Represented with small r. What is the range of small r? The range of small r is -1 to +1. If I take only the magnitude of r, r lies between 0 to 1 only. Minus and plus indicates the direction. Whether it is upward or downward, you'll get the information by the symbol, the sign. Minus represents downward direction, plus represents upward direction or positive direction. Then, we quantify strength based on thumb rules. What are the thumb rules that we have? R greater than 0.85, we say strength is strong. R less than 0.4, we say strength is weak. And if R lies between 0.85 and 0.4, we say strength is moderate. That's it. So this is what we have understood in the last class. And let us take our discussion to the next level. I'll move a bit. We have completed EDA and we'll jump into data cleaning, data pre-processing steps. As I have given the overview of all the 9 steps in the yesterday's session, today we'll be understanding each and every step to its depth. Okay, so all the steps and the explanation, theoretical explanation along with the hands-on will be covered in today's class. So that will be the agenda for the day. Now, let me start. As usual, first of all, let us understand the different names for data preprocessing. Also called as data cleaning. It is also called as data wrangling, also called as data munging, also called as data organizing. We are organizing the data. Okay, so all of these mean same. What we are doing in short, we are cleaning the data. Data might have duplicates, data might have outliers, data might have missing values. So you cannot feed this data as it is to build your model. No, not accepted. Then what I am supposed to do? You are supposed to apply some cleaning steps. Clean the data, then go and build the model on the clean data. What if you don't clean the data? Your results will not be good. Results? Yes, it means output, guys. It means the output that you are expecting, the predictions, will not be up to the mark. Okay, so that is why cleaning steps are mandatory and they are very essential. I hope it is making sense. Let me start with the first step. It is typecasting. It is typecasting. What exactly is typecasting? Typecasting is nothing but converting one data type to other. If I want to convert the data type, okay, from one type to the other type, I'll perform typecasting. Simple. There is no huge concept related to typecasting. It is very small step, and typecasting can be achieved using as type function. Using as type function, we complete this typecasting. Okay. Now, let me take a data set for hands-on, and as usual, we'll proceed with the spider. I'm using spider. Again, I'll suggest you spider if you are a beginner. If you have good amount of knowledge, if you have good hands-on experience, then choose your own IDE. But my choice will be spider. Okay, right. What am I doing? First of all, in order to perform typecasting, there should be data, right? So in order to read this data, I'm importing pandas. What is pandas? Pandas is a package. It is a package which help us for data manipulation. Okay. So what am I doing? I'm importing pandas. I'm importing pandas as PD. So that means I'm giving an alias name to pandas. Done. So that means pandas got imported. Now, for this entire data cleaning steps, I have took cars data, which is open source, readily available in Kaggle. Okay, even you guys can download it and start working on the data cleaning steps. Right. So this cars data, I have it in this location. Okay, at this location, I have the data set, and this data is in Excel format. It is stored in Excel format. It is not in CSV format, guys. So as the data is in Excel format, I'm using read underscore Excel function. It is not read underscore CSV. Read underscore Excel from pandas. PD dot read underscore Excel. So PD, what is PD? Pandas. Read underscore Excel is a function from pandas. So it is representing the hierarchy. The dot is representing the hierarchy. So when I execute line number 14, the data which is present in this cars Excel file, the data gets read and it stores in an object cars underscore data. So let me do it. Is it done? Yes, it is. Cars underscore data is the variable name. The type is data frame. What is data frame? Data frame is a two-dimensional object in Python. which is similar to table, which is similar to table. So we'll have both rows and columns, 428 rows and 14 columns. Right. Let me open the data set first of all. Let me show you the data set. So this is the data set that we are working on, in which we have 14 columns, make of the car, make of the automobile. So this data set is related to automobiles, cars. Okay. So make followed by model of the car, then the type, either it is an SUV, sedan, mini, micro, you'll get all the different types. Then the region, okay, and the type followed by engine size, so on. So these are, different. Yes, these are the different features that we have. Okay. Yes, these are the different features that we are going to work on, and data dictionary is also provided, guys. If you see here, so make represents the manufacturer of the car. Model represents specific model of the car. Okay, because there are different companies, different manufacturers, and each manufacturer comes with different models, obviously. Then we are going to understand the type of the car, whether it is an SUV, sedan, pushback. Okay, like we have hatchback, right? So there are multiple types. So we'll understand the type of the car, then the origin of the car. Okay, the country or the origin, the region of the origin. Okay, then followed by drivetrain. We'll have front and rear type as well as all. So MSRP represents manufacturer suggested retail price. As this data set is collected from US, United States, so you'll find the price in dollars. Okay, so the price that you observe here is in dollars. Then next to it we have engine size, cylinders, the number of cylinders within the engine, then the horsepower of the engine. MPG is calculated in two different ways, within the city and on the highway. Okay, MPG represents miles per gallon, right? Then finally we have weight of the car. So it is in FPS system, pounds. Wheelbase, the entire wheelbase in inches. And finally the length of the car. Okay, if we observe the chassis, taking the length of the car is what we have in length column in inches. So these are the 14 columns on which we are going to perform data analysis. I mean data cleaning. Right. So let me get the data types first. Let me get the data types of all the columns. In order to get the data types, we have an attribute. It is D types. There is an attribute D types. Cars underscore data dot D types will return as the data types. For all the columns, it will return the data types. See. So I can clearly observe the first few columns are non-numeric. Object represents they are non-numeric data. And rest of the columns are numeric. Right? Under numeric, again, we have int and float, both. Int type columns and float type columns. Now, what am I doing, guys? Let us focus. Cars underscore data is my data frame. It is my data frame. So from this data frame, I'm going to work on engine size column. I'm going to work on engine size column. Right. So what is the type of engine size? It is float. I don't want to have the values in float. Okay. So that is why I want to change it to int. I want to change it to int. So if I perform this, type conversion will be done. The type casting will be done. From float, the values will be converted to int. Let us Before executing, let us have a look. Engine size, you observe the values in float. Yes, the values are in float. Now, I'll perform this execution. The line gets executed. And where am I storing the results? I want to store the results in the same data frame in the same column. So it actually rounds down. If you observe, whatever the values that you have earlier, the float values got converted to int values. Done. Job done. That's it. This is called type conversion, typecasting. This is called typecasting. Now, let me cross check. After performing typecasting, let us check the D types again. For engine size, it should be int. Yes. So the typecasting has been done. That's it. In the same way, can I also perform typecasting once again? Yes. If you see MSRP column, what is MSRP? Maximum suggested, manufacturer suggested retail price. So the manufacturer will suggest some retail price, the price. Yes. So this price column is actually in, the values are in integers. I want to change the type to float. Will that be done? Yes. I'm performing typecasting and the results will be stored back to the same column. I'm going to store the results back to the same column and see what happens. Done. If I open the variable, if I open the object, the data frame, you see here, earlier all the values are in integers. But now it became float values. They became float values. So this is how we perform type conversion guys. Typecasting will be done in this way. That's it. It is very simple. So I can clearly understand post conversion MSRP column got converted to float. Now, let me go with the second step under data pre-processing, data cleansing. It is handling duplicates. It is handling duplicates. Is it possible to handle duplicates? Yes. First of all, what is a duplicate? Duplicate represents the rows with identical data. If there are two rows in which all the values are same. If there are any two rows, if you see row record 0 and record 1, index 0 and index 1, they are not duplicates. Don't just assume that the make is same. Even though the make is same, the model is different, right? So it is not identical data. All the columns should have the same values across the two rows. Then we say they are duplicates. This is not a duplicate. Okay. So we just have the make as same. That doesn't mean that these records are duplicates. We'll identify such kind of duplicates and these duplicates have to be removed. What is the use of having duplicates? There is no purpose of having duplicates. Now, what I'll do is, for this duplicates, we have created a data set, a dummy data set, taking this cards data, we have created a data set in which I have added some duplicates. Okay. So let me read this data. So this data is present in a CSV file and I'm going to read it using read underscore CSV function. Done? Yes. Earlier it is 428, 428 comma 14, but now it became 431 records comma 14. Right. So that means there are duplicates. In order to identify duplicates, there is a function called duplicated. There is a function called duplicated. This duplicated function will return us a Boolean series. It will return us a Boolean series. What is this series? Series is again a one-dimensional object in Python which contains multiple rows but only one column. It returns only one column. In this series column, you will have the Boolean values, guys. Boolean values means true or false. So what can you identify from that? You can identify whether it is a duplicate or not, is what you can understand. Right? So let me execute line number 65. The results got stored in duplicate variable. You see here, duplicate is a series and what is the size? 431. 431 rows. But do you see columns? By default, series means one column. And duplicated function will return us a Boolean series. So what does false indicate? That means they are not duplicates. Wherever you find true, it means a duplicate. It means record 27. Index 26 means record 27 is a duplicate. That is what we can understand. But this duplicated function is just identifying. This is just identifying. But what is our aim? What is our agenda? We have to remove the duplicates. Right? So, if you want to print the values present in the duplicate variable, yes, you can print a duplicate, then the results will be printed to the console. The results will be printed to the console. Anyhow, it will not result as all the values. So obviously, when you are trying to understand the data, obviously you can use head or tail function, that is fine. But apart from Spider IDE, when you try to print, you'll get in this fashion. See. Now, what if I ask you how many duplicates are present in the data? Duplicated function, it is returning as a Boolean series. Fine, guys. But is it also giving an information regarding number of duplicates? Are we getting the information for number of duplicates? No. But I can use the logic of sum. If I perform sum of the values present in this series object, will I get the number of duplicates? Yes. How come? Because we know false is internally referred as 0. True means 1. So that means when I add all the values present in this object, series object, okay, and if I get an X number, that X number represents the number of duplicates. Am I right? Yes. So let me perform sum of duplicate function. If I perform sum function on the duplicate object, series object, it has returned me the value as 3. That means there are 3 duplicates, guys. See, total number of duplicates are 3. Now we are supposed to handle these 3 duplicates. We are supposed to handle the 3 duplicates. For handling the duplicates, there is a function. It is drop underscore duplicates. It is drop underscore duplicates. What does drop underscore duplicates does? Drop underscore duplicates function will drop the duplicates wherever we have the true. Okay, within this series object, wherever we have the true. Okay, so those records gets dropped. Let me show you an, record with the true value. See, index 430, it is a duplicate. Yes, it is a duplicate. So when I perform drop underscore duplicates function, the records where the values are true, which has the values as true, they get removed. They get dropped. Let me perform. So I'm taking the data frame object in which we have duplicates. Then I'm going to use drop underscore duplicates function. So this drop underscore duplicates function will drop the duplicates. And where am I storing the results? Data underscore first. Data underscore first. So this will return me, the data set without duplicates. You see here, just compare. Both of them are data frames, but see the size, observe the size values. Earlier it is 431 records, but now you see only 428. So what happened? I can clearly understand that the 3 records which are duplicates, they got removed from the original data. From this data, 3 records were being removed. For clarification, for better understanding, open the result of drop underscore duplicates. We know that the last record is a duplicate. Yes. So scroll to the down. Go down. Yes. Do you find 430 record? No. Index 430 was missing. Why? Because it got dropped. As it is a duplicate, it got dropped. In this way, we can clearly understand wherever there is a missing index, that record was being dropped as it is a duplicate. Okay, so it is not possible to understand for each and every record, right? See, as this data set is just containing only 400 records, we are, able to do it. We are able to understand which record got dropped. But if you have millions of records, will you do in the same approach? Not exactly. Right. So in real time, when you work in real time, you will work on millions of records. Okay. So this will, help you to understand how the duplicates are removed. Even if you see here, we have index 25. Next to 25, we have index 27. What about 26? Index 26 was a duplicate, guys. Because of 26 being a duplicate, it got removed. It got dropped by drop underscore duplicates function. Making sense or not? Are you able to get the point? What I'm trying to convey? So initially, when you are practicing, do it on a small data set so that your understanding will be clear. Okay. So when you compare the results, you can clearly understand, okay, 26 is a duplicate. Because of 26 being a duplicate, it got removed by drop underscore duplicates function. If you still don't believe me, open duplicate series, the series object, scroll down, you should see true value for index 26. So that means index 26, record 27. Index 26 means record 27 is a duplicate. It is a duplicate. Clear? Yes. So we understood how to handle duplicates as well. Then the third step, next to handling duplicates, the third step in the sequence is outlier treatment. What are outliers? Outliers are nothing but extreme values. Outliers are nothing but the extreme values in the data. So what happens if you have extreme values in the data? we know that extreme values will actually make the data skewed. We understood, right? When we are discussing the concepts of third moment, business decision, or histogram, okay, I can clearly understand that data becomes skewed if there are extreme values, if there are outliers. And what happens if you have outliers in the data? When you have outliers in the data, the model performance. We are going to train the model using this data. Yes. So as part of the training journey, the model understands, learns from these data, and because of these outliers, the performance of the model will not be maintained. It affects the model's performance. That is why we have to treat outliers. That is why we have to treat outliers. Okay, but which plot will give us the information about outliers? Which plot it is? Box plot. Box plot is the only visualization which gives the information about presence of outliers. For performing outlier treatment, I'm coming up with required packages, guys. So let me import pandas for data manipulation. Then next to pandas, I'm going to import NumPy for handling arrays as well as for basic mathematical calculations. I'm importing NumPy as NP. I'm importing NumPy as NP. NP represents a shortcut name, an alias name. Right. Then next to NumPy, I'm going to import PyPlot. We are going to import PyPlot from Matplotlib. We have a package called Matplotlib for data visualization. Within this package, I just want to import only a module called PyPlot. I want to import only a module called PyPlot. So I'm importing PyPlot as PLT. An alias name is what we are providing to PyPlot. And finally, I'm going to import Seaborn as SNS. I'm going to import Seaborn as SNS. So what is the purpose of Seaborn? Even Seaborn is also used for data visualization only. What makes the difference between Matplotlib and Seaborn? Matplotlib is a basic visualization package. Seaborn is a advanced package. It is an advanced package. So let me import both of these two. Done. Then I'm reading the data, the same cars data. Okay. And I'm storing the data present. I'm going to store the data in an object. It is df. So df becomes my data, guys, now. df becomes my data in which there are 428 records and 14 columns. Now, first of all, in order to treat outliers, we should get the information whether we have outliers or not. Am I right? Yes. So that means we have to visualize a box plot. We have to visualize a box plot. But the question raises, we know that box plot is a univariate plot. Box plot is a univariate plot. So taking one column at a time, we tried visualizing box plot yesterday. But here, how many columns you observe? There are 14 columns. Out of 14 columns, the first 5 columns are non-numeric. That means we cannot visualize box plot on non-numeric columns. So let me remove 5 from 14. That means 9 columns. So if I want to visualize box plot, I can visualize them one by one. I'll visualize box plot on MSRP, then engine size, then cylinder, so on. That is time consuming. Am I right? I have to visualize 9 box plots because 9 numeric columns. Instead of that, let us visualize box plot on all the columns at a time. Let us visualize box plot on all the columns. Is that possible? Yes, it is. What am I going to do here is, I'll take a function called plot. There is a function called plot. So this plot is the function that I'm going to use on the data frame object df. On this data frame object df, I'm taking the function plot and I'm mentioning here clearly the kind of plot that I want to use is box. That means it takes box plot into consideration. I'm going to visualize a box plot. Next to it, the next parameter is figure size. The size of the figure should be 12 by 8. That means 12 in width, 8 in height. Height of the plot is 8. Would you like to get any subplots? Yes, within one figure, I would like to get subplots. So that means, again, all the 9 columns, all the 9 numeric columns that we have, I'll visualize in one single plot, guys. So within one single plot, I will get subplots. Okay. Then next to it, we have Sherry. Sherry represents whether to share the y-axis or not. I'll keep it as false. The reason behind why we kept Sherry is equals to false is, no, the y-axis should not be shared because, each and every column have its own scale. MSRP contains very big values, but engine size contains very small values. If I keep the share is equals to true, the y-axis will be shared across all these subplots, where we cannot interpret the results properly. Making sense? Then, colors also I'm defining. For boxes, it will be blue in color. For whiskers, I want whiskers in orange color. The median should be in black in color. And caps, I want it in red color. I have specified the colors for all these different parts of box plot. And patch artist is equal to true represents it fills the box. The box will be filled with the color. And show flyers represents whether to show outliers or not. Yes, obviously I want outliers. To display outliers, so I'll keep it as true. We are not done. We are not done yet. I'll go to the next line where you see here PLT dot subplots underscore adjust. PLT represents pie plot. Yes. From pie plot, we have a function called subplots underscore adjust. Subplots underscore adjust. So this will help us to adjust the subplots by keeping the width space, the space between the plots as 0.8. And the title for the overall plot, I'll keep it as box plot for all numeric columns. And finally, show function to display the plot. So I'll execute all these lines of code together, and this will return me, the box plot. This will return me the box plot, guys. Let me go to plots. I'll undock it. Just give me a minute. This is not. Yes. Can you see the plot? We have got the box plot for all the columns at a time. And can you observe outliers in all the columns? Yes. MSRP have outliers, engine size have outliers, cylinders have outliers. All the columns have outliers. All the columns have outliers. So that means we have to focus on all the columns. But Let me take one column and let us understand the technique. There is a method called Winsorization. What it is? Winsorization. This Winsorization helps us to treat the outliers, where the outlier values will be capped. It will be capped. So if there is a outlier, okay, so that outlier value will be replaced with the limits values. That is what Winsorization does. And this Winsorization, we have to get it from a package called feature underscore engine. Feature underscore engine. From feature underscore engine dot outliers, the module, I just want to import only a function. It is Winsorizer. It is Winsorizer. So let me do it, guys. Is it done? Yes. I have imported Winsorizer. Now, I will initialize the Winsorizer. Okay, by specifying the method that has to be used. This Winsorizer should use the method IQR. What is IQR? IQR represents interquartile range. IQR represents interquartile range. And I want to treat the outliers at both the ends. At both the ends, I want to treat the outliers. And the fold value that I want to keep is 1.5. So in the formula, we are using the fold value Q plus or minus 1.5 times of IQR. So that 1.5 is nothing but fold. And on which variable I want to use it? Let us try usually on the MPG column. Let us try it on the MPG column. Okay, so I'm initializing the function and I'm storing this function to an object, Windsor underscore IQR. So I have to execute all the lines of code together and I have initialized. Done. Okay, so now I'll start using the function. The function got initialized. I'll use the function. Where is the function? The function is present in this object. Windsor underscore IQR dot fit underscore transform on MPG city on this column. I want to perform Winsorization. So this fit underscore transform function will actually fits the function on this column and it will transform the results. It will return the transformed results. Where I want to store this transformed results? I want to store this transformed results to a new column. In the same data frame DF, I want to add a new column. What it is? MPG underscore city underscore IQR. So when I execute line number 124, how many columns will it become? 14 becomes 15, guys. The reason behind it is, see, it added a new column. There is a new column into the data frame. What it is? The new column is MPG city underscore IQR. You see in the last one, which is nothing but the output of the Winsorizer technique. So if I perform box plot on this column, I will not get any, it will not return me any outliers. See, what am I doing next to it? SNS.boxplot. I'm going to visualize box plot on the new column that we got. MPG city underscore IQR. Now let me visualize the box plot. Do you observe outliers? No. What happened? The outliers got treated by Winsorizer. Earlier, we have outliers. See, if I open the plots, MPG city. Are there outliers? Yes, there are outliers. But next to performing Winsorization, do you find outliers? No more outliers. No more outliers, guys. Making sense? That is how we handle or treat outliers. Making sense? So this capping method under Winsorization have multiple methods. There are multiple capping methods. Widely used method is IQR. We also have Gaussian method. Gaussian method means Z distribution, Gaussian distribution, Z. Okay. So this Z distribution or Gaussian method takes the fold value as 3. And how can you get this information is, you have to go through the documentation of Winsorizer. If you go through the documentation of Winsorizer, only then, you'll understand the function and the parameters to the depth. Only then you can work on it. Now, let me initialize Winsorizer with Gaussian method by keeping the fold value as 3. Let me see what happens. I have initialized. I'll perform the same. I'm going to use this Windsor underscore Gaussian. I'll make it to fit on the MPG city column. Okay. And where am I going to store the results? I'll store the results to the new column. It is MPG city underscore GAU Gaussian. So 15 becomes 16 now. See, a new column got added again. The last column is nothing but the results of Gaussian distribution, Gaussian capping method. And the results will not be same. IQR and Gaussian, as the formulas are different, obviously the values will change. If you see here. Okay, right. Let me visualize box plot on the new column. So even now, if it fits well, it will not return the outlier. See, if you see here, even after performing Winsorizer, I still see outliers. That means on MPG city column, Gaussian method is not actually fitting the data. So this is like an experiment that we do. Anytime you cannot tell, that IQR method works well for this data or Gaussian method works well for this data. No one can tell that. Okay. What you have to do is, we have to experiment. When you experiment with the different methods, and if the outliers got treated, that will give you the best technique for that specific data. Making sense? So in this way, we do lot of experiments by taking different methods. There is one more method called quantiles. Okay. So even this is also an experiment, guys. Just to explain you what is the difference between these three techniques is, the method is being changed. IQR, Gaussian, and quantiles. That's it. That's it. Okay. So we do experiments. We'll try to figure out the best one. Whichever method gives the best results, finally we'll consider that specific method. That's it. Our aim is to handle the outliers. Our aim is not to, work with IQR method or Gaussian method or quantiles method, or even we have MAD, mean absolute deviation method. Okay. So not these methods. Our aim is to treat the outliers, handle the outliers. Now, next to outlier treatment, we have zero and near zero variance. We have zero and near zero variance. What is variance, guys? What exactly is variance? Did we understood variance so far? Focus. Variance represents the spread in the data. The average spread in the data is what variance represents. But if you find a data set which does not have any variance, okay, if you secure the same marks in all the subject, If you secure the same marks in all the subject, okay, will there be any variance in it? No, right? No, obviously no. Okay, so even your average mark will be same. Assume that you have secured uh, 80 or 75 per 100 in all the subjects. 75 in math, 75 in social, 75 in science, so on. Okay, so if I ask you to calculate average, your average will also be 75. Am I right? Yes. Why? Because there is no variance. There is no spread in the data. There is no spread. So, the main reason behind calculating variance, this step, zero and near zero variance is, we'll identify the columns. We'll get the columns information which contains zero and near zero variance, and we'll try to remove them. The reason behind it is, if there are columns, such kind of columns, we cannot do any kind of analysis. We cannot get the information. Okay, we cannot get this information properly. We cannot perform the analysis. Okay, now let me calculate variance as usual. Okay, so I'm going to import pandas. I'm importing pandas as PD. Then next to it, I'm going to read the data from an Excel file. Okay, it is cars data, again the same data. I'm going to read the data using read underscore Excel function. I'm using read underscore Excel function and from pandas, and the data is being stored in DF. But before that, let me clear the memory. Python's memory is what I'm clearing first of all. Okay. It's taking time. Yes, it is done. Now, let me import pandas once again. Let me import pandas. Next to pandas. What is the purpose of pandas? Pandas help us for data manipulation. To manipulate the data, we use pandas. Then I'm reading the data from an Excel file. Okay. So we use read underscore Excel function from pandas. And this is the data, the path at which we have the data. Cars.xlsx. Post reading this data, the data gets stored to an object. It is DF. It is DF. See what's happening. So the size of the data set is same, 428 records and 14 columns. And let me get the D types. D types will return what? D types will return as the data types. For each and every column, it returns the data types. So let me get the data types for all the columns, guys. Now, let me calculate variance. We know to calculate variance, there is a function var, var. Var is the function which returns us the variance values. It returns the variance values. df.var function will return the variance. So at a time, I will get the variance calculated for all the columns. As I did not specify one single column, this will return me the variance for all the columns at a time. Right? So where am I going to store the results? The results will be stored to variance, a variable variance. Done? And if you see here, variance is a series object in which It contains 9 values, the column names and the variance. The column names and the variance. Right. So let me print this variance to the console. The values that we have within the variance will get printed to the console. Now, tell me, do you observe any of these values? The variance values for any of these columns? Do you observe the variance as 0 or near 0? Try to understand. By looking at these values, do you find any of these values are 0 or near 0? Yes, you are trying. No. The answer says no. Why? That doesn't mean it is not 3.7. 3.7 into 10 power 8. Okay. E plus 0.8 is there, right? This is read as 10 power 8. So that means 3.7 into 10 power 8. Is that 0? No. But here I see 1.2 into 10 power 0. Right. So obviously this is close to 0. 1.2 is close to 0. But it is not 0, guys. Even in cylinders, it is 2.4. That is how you have to interpret the results. Okay. Now, after concluding it, I can understand that none of these columns have the variance as 0. The variance as 0. Now, what I'll do is, for cross-checking, I will go with relational operator. What is this relational operator that we are using here? Can you identify which relational operator we are using in line number 178? Double is equals to is nothing but is equals to operator. Double is equals to is nothing but is equals to operator. So what we are checking here is we'll get the variance, right? So we are asking whether these values are they 0 or not. If the variance value for any of the column is 0, it returns true. If it is not 0, it returns false. Now let us check. Do you find true anywhere? No. So that means none of these columns have the variance as 0. None of the columns have the variance as 0. So I need not remove any of the column. But again, coming into the point, we also have it as near 0, right? You can ask the question. See, we have none of the column, the values as 0. The variance value is not 0. But there are few columns like engine size, cylinders. Okay. These columns have the variance value close to 0. 1.2, 2.4. But why will not drop such kind of columns is when you want to drop a column in real time, we have subject matter experts, guys. We have SMEs, subject matter experts. These subject matter experts, what they do is before we taking any decision, you know, excuse me, before taking any decision, we'll cross check with them. We'll get the approval. We'll discuss whether such kind of column should be dropped or not. But we can clearly understand engine size and cylinders are two important columns related to, automobiles. The case, not just dropping. You have to also map your case. You have to map with your business problem. Only then you can take the right decision. Clear? 0 and near 0 variance. Next to 0 and near 0 variance, we have discretization, binning, or grouping. We have discretization. binning or grouping. So any idea what is discretization? Do you guys have any idea regarding discretization? Not exactly? Okay, let me tell you then. Discretization is nothing but, it's a process of converting continuous data to discrete data. If you have any continuous data, okay, and if you want to convert this continuous data to discrete data, that is called discretization. Even histogram performs discretization only. You'll get bins in histogram. Yes. So that is nothing but you're converting your data into discrete data, bins. So let us understand how discretization is performed. I'm importing pandas. Okay, I'm importing pandas for data manipulation. Then I'm also loading the data again. Okay, so the data is present in an Excel file. I'm using read underscore Excel function to read the data, and the data gets stored to a variable. It is data. The data gets stored to a variable. It is data. So within the data, I have the data, the car's data. Now, let me perform discretization. In order to perform discretization, we have a function in pandas. It is called cut. It is called cut. pd.cut performs discretization. But how it is going to perform discretization? The bins is, let us understand now. pd, from pd, I'm using the function called cut. Within the cut function, I'll pass the parameters one by one. What is this parameter? This is nothing but the data. This is nothing but the data on which I want to perform discretization. So I'm going to work on engine size column from data. From this data frame, I want to perform discretization on engine size. So I'm taking engine size column data. Then I'm defining my bins. I'm defining my bins. How many bins? Let us understand. These bins in total have, the first bin should start at minimum of the engine size column values. Min function will return the minimum of the column. Yes. Min will return the minimum value of the column. Then next to it, I'm going to capture the mean value for that column. Next to it, I'm going to capture the max value of that column. So, how many bins it is going to give us is 2 bins. How come 2 bins? Min to mean will return as 1 bin. Bin will have both minimum value, maximum value. It will have both the minimum value and the maximum value. So this will return me the first bin. In the same way, this will return me the second bin, the values for my second bin. So in this way, we'll get 2 bins. And these 2 bins will take the labels as low and high. It will take the labels as low and high. Now, let me execute all these lines of code together. Okay. And where am I going to store the results? I'm going to store the results in a new column. It is engine size underscore new. Within the same data frame, I would like to add a new column engine size underscore new, in which you will find the discrete values low and high. Depending on the value, that value falls into the bin and it returns the label. Done? Is this done? Done. Now let me open the data frame and show you the results. See. These are the results that I got. Low. Why it is low? Because it is falling under the first bin. 2, 2.4, 1.8, 1.8, so on 3, all of them are falling under the first bin. Accordingly, you'll get the label as low. Clear? But the problem that we get with the cut function here is it does not include the lowest value. The lowest value will not be included by default. Okay, so in order to get the value counts of each and every type, there is a function called value underscore counts case. This value underscore counts function will calculate these distinct values present in the column, and it will also return the count of the distinct value. It will also return the count of distinct value. So let me execute line number 201 so that you'll understand what are the distinct values that we have in the engine size underscore new. There are only two values, low and high. The value for the count for low is 219 and for high it is 207. When you sum up these two values, you will get 426. You get 426, but it should be 428. It should be 428. Why it is not returning us the two values is, by default, cut function will not include the lowest value. So what I'll do is, I'll perform the same, but I'll come up with an additional parameter. It is include underscore lowest. The lowest value by default will not be included. It will be false. So when you keep it as true, that lowest value will also be included when you perform discretization. So I'll do the same, and this is called binarization. This is called binarization. What is the difference between discretization and binarization is, binarization is nothing but converting into two bins. Discretization is having, converting the continuous data into discrete data in which you have more than two bins. That is called discretization. But this is an example of binarization. Making sense? Yes. Now let me perform discretization. See. Let me perform discretization. So within this discretization, I should have more than two bins. I'll take the same engine size column. And I'm defining my bins. Try to understand the bins, guys. First of all, the first bin starts at the minimum value of the column, and it ends at the 25th percentile of the column, Q1. So from min value to Q1 will return as bin 1. It will return as bin 1. From Q1 to average, nothing but the median value, the 50th percentile value will return as the bin 2. Okay. From Q2 to Q3, 75th percentile will return me bin 3. And from 75th to maximum value, it will return the bin 4. So in this way, I am performing discretization, and I'll also provide the labels for 4 bins: small, medium, large, extra large. So this is an example of discretization. This is not binarization, because here I am getting more than 2 bins. Earlier, it is an example of binarization. Where am I storing the results? I am storing the results in the same variable, in the same data frame. Okay. Within the same data frame, I am going to add a new column, engine size underscore multi. Okay. So under this variable, I am going to store the results. Let me execute all the lines. If you observe properly, 16 became 17. So let me open it. So this is the output of discretization. This is the output of discretization. Right. Let me also get the value counts. It should match as we are including the lowest. It should match. See, if you add up all these values, you'll get 428. Give a try. 100, 100, 100, 100, 400, 14 plus 7, 21, 21 plus 4, 25, 25 plus 3, 28, 428. So it is matching, right? Yes. So that is what discretization means. In short, discretization means converting continuous into discrete data. Converting continuous data into discrete data is called discretization. Now, let us move to the next step. It is dummy variables or feature encoding. Dummy variables or feature encoding. What is the use of dummy variables or feature encoding? We'll understand now, guys. First of all, what exactly is dummy variable? Means variable represents columns. Am I right? Variables represents columns or features. So we are trying to make dummy columns. We are trying to make dummy features. But why should I make? Why should I create dummy columns? That is the question that comes first of all, right? If that is your question, in general, the next step is model building. Yes, in which we are going to build a model y is equals to f of x. As part of model building, in order to build an equation, we generally include only the numeric columns. We generally include only the numeric columns. But what if I want to include a non-numeric column? If there is any non-numeric column, and if I want to include it as part of the model building part, how it is possible? We know that a non-numeric column cannot be included in an equation. Am I right? Yes. I'll give an example, guys. See, if there is a use case, if there is a project like, I want to predict whether a patient have disease or not, whether a patient have cancer or no cancer. This is my use case. Okay. Now, in order to build this, in order to predict for the new data, for the new patients, first of all, I have to build a model. I have to build a model, and using this model, I can predict on the new data. But when I go to the historical data, obviously I'll have the features related to the disease, nothing but the cancer. One of the column might be gender. Yes, obviously. Under gender, what kind of values you will have? You will have male or female. Male or female. If you have a column like male, female, okay, and if you want to include in this model building part, tell me, is it possible? First of all, no. Why? What does male means in this equation? We know male is a human, female is a human. We can understand it, but model, it cannot understand. It is an equation that is being formed in the backend. So, we know that this is an important column that has to be included. We cannot drop it. I have to include it. Then comes the concept of dummy variables. Then comes the concept of feature encoding. We create dummy columns for this gender column. We create dummy columns for this gender column. How? There are techniques like one-hot encoding or label encoding. This one-hot encoding, label encoding help us to convert a non-numeric column to numeric column. Once if this non-numeric column is converted to numeric column, can I include this numeric column in the equation? Obviously, I can include. I can include this column as is. So that is the purpose of creating dummy variables or dummy columns. Now, so before we understand one hot encoding, label encoding, let me load the data set as is. I'll clear the memory once again. Okay. I'm clearing the memory. Once after clearing the memory, we'll start, guys. Right. Is it done? Yes. I'm going to import pandas as PD. Why do we import pandas? For data manipulation. Done. Then I'm reading the data, same data that we have in the Excel file. Okay, using read underscore Excel function from pandas and storing the data in DF. I'm storing the results to DF. Done. Now, what I'm doing next to it? What am I doing next to it? I'm using a function drop. I'm using a function drop. So this drop function will help us to drop the given columns, the specified columns. What columns I'm going to drop here? I'm going to drop make and model columns which are not relevant. See, I can drop the columns which are not relevant. Okay, so such kind of irrelevant columns can be dropped. Axis is equals to 1 represents that the specified values are columns. Okay, so axis takes zeros and ones. Axis parameter take 0 and 1. 0 represents it is rows. 1 represents they are columns. So I'm going to drop the make and the model columns from the data frame and storing the results to df1. I'm done. I can perform the same action. I can perform the same dropping action. Okay. Using in place parameter also, guys. Using in place parameter. That is inside drop function. So when you say in place is equals to true, that means you are dropping the columns and you are storing the results back to the same variable. In place actually performs within the variable, but here it is not performing within the variable. If you observe df is of same size, only df1 results got shared, changed. 14 became 12. Right? So even I'll give a try. I'll convert the df to 12. See. Done? Yes. Now, let us come up with the first technique of encoding. What is the first technique under encoding? Okay, I'm using get underscore dummies. Get underscore dummies is what I'm using. Okay, so this get underscore dummies function will help us to return the dummy columns. How? I'll explain you. So, if there is any column like gender, let me take a non-numeric column gender and the values female, male, female, male or male, female. In this way, we'll have the values. This is how we have the values. When I perform get underscore dummies, when I perform get underscore dummies on this column, it will actually count, it will identify the distinct categories in this column. How many distinct categories we have? We have two distinct categories. What are they? Female and male. So the columns will be given as gender underscore female, gender underscore male, gender underscore female, and gender underscore male will be given as output, in which we'll have the results like female, wherever the value, if it is identifying as female, gender under the gender underscore female, it will return 1. But under gender underscore male, it will return 0. Why? The original value is female. In case of male, it will return 1 for gender underscore male, but for gender underscore female, it returns 0. So this is how it returns ones and zeros only. It returns ones and zeros only. You cannot expect any other number as part of the output for get underscore dummies. But how many columns will be written? How many columns? The number of columns will be dependent on the number of categories in the non-numeric column. If there are 2 categories, we'll get 2 columns. If there are 5 categories, we'll get 5 columns. Making sense? So that is how get underscore dummies work. And even after dropping the first column, I can still interpret the results. How? Is if you have the output in this fashion, if I drop the first column, gender underscore female, if I drop the first column, gender underscore female, can I interpret still? Yes. Because if you see here, if the value is 0, obviously under gender underscore female, the value would be 1. Under gender underscore female, the value would be 1. If the value underscore gender underscore male is 1, obviously under gender underscore female, the value would be 0. So in that way, even after dropping the first column, I can still understand the results. I can still interpret the results. So what exactly, why should we drop the first column is, to reduce the dimensionality, to reduce the data output dimensionality, we actually, perform the drop underscore first. The first column need to be dropped. Right. Anyways, let me execute. This is how get underscore dummies work. I'm performing get underscore dummies on the data frame. I'm passing the entire data frame, guys. The original data frame is what I'm passing. And this get underscore dummies is from pandas. Okay. And we are going to store the results to get df underscore new. We are going to store the results to df underscore new. So, see, observe the variable explorer. What happened to the results? 12 became 21. How come it is? It is because of the number of distinct categories. See, these are my numeric columns. It does not touch numeric columns. Only the non-numeric columns will be converted. We have a column called type. So type got converted to, see, different columns. There are we got different columns as output for type. 6 columns, type underscore hybrid, type underscore SUV, type underscore sedan. Again, you might raise a question. Why only in this fashion? Why not type SUV underscore type underscore SUV as the first column? If that is your question, the output will be given as, it follows the alphabetical order, guys. It follows the alphabetical order. Out of hybrid and SUV, obviously hybrid comes first. Okay, so that is why hybrid comes first, then SUV, then sedan, so on. Making sense? Yes. Can I reduce the dimension? Yes, by dropping the first column. By dropping the first column, I can reduce the dimension at least. For each and every column, I can drop the first column. So the results I'm going to store to df underscore new underscore 1. So 21 became 18. So that means 3 columns got dropped. Clear? Yes. Now, we understood get underscore dummies. There is one more technique called one-hot encoding, which is similar to get underscore dummies. So df.columns attribute, columns is an attribute which returns the column names. Okay. So df.columns will return the list of columns that are present in the data frame df. See. So these are the list of columns that we have within the data frame. Now, I'm going to import one hot encoder from sklearn.preprocessing. From sklearn.preprocessing, I'm importing one hot encoder. To perform one hot encoding, we use one hot encoder function. Done. Imported. So this one hot encoder I'm initializing where I would not like to get the sparse output. Sparse means empty, right? So I would not like to get the sparse output. So I'm keeping it as false. I'm initializing the function. Done. Now I'll start using this one hot encoder on the data where I would like to use it only on the first 3 columns. First column, second column, and the third column. Why? Why not the other columns? The rest of the columns are numeric. Only the first 3 are non-numeric. Making sense? Yes. So I'm going to fit one hot encoder using fit underscore transform, and the result will be an array. So I'll convert back it to data frame. The result of this one hot encoder will be an array. It will be an array. So I want to convert it back to data frame. I'm using pd.dataframe function. And the column names, I would like to get it from get underscore feature names out. Okay, this is the function that we use from one hot encoding. Okay, which help us to return the column names for the output. Let me show you the output of one hot encoding. It will be similar to get underscore dummies, but the difference that you observe is get underscore dummies is a function from pandas, but one hot encoding is a function from scalar. See, if I open it, you'll find the output same, zeros and ones is what you observe. It will be similar. There is no change, no difference, but a bit difference you observe is with respect to the package. Then finally, I can concatenate the results. I can combine the results because I was working only on the non-numeric columns, right? I'll combine the results of the one hot encoding and the numeric columns. I'm using concat function, and this concatenation should be done via columns. Axis is equals to 1 represents columns. So the concatenation will be done and the output will be stored in OHE underscore output. Done. So this is my output, final output. Is that similar to one hot encoding? Get underscore dummies? Yes. There is one more method called label encoding. Instead of returning n number of columns as output, label encoding returns only one output, one column, guys. In case of one hot encoding, It is resulting us in n columns, right? But label encoding will return us only one single column as output. Okay, even though if I have n categories, still it returns only one column as output. It returns only one column as output. But what will be the values? The values will depend on the number of categories. If I have 5 categories, the values will be from 0 to 4. 0, 1, 2, 3, 4. If I have 3 categories, I'll get the values like 0, 1, 2. In that way, I'll get the output for label encoding. So let me import it and I'll show you the difference between label encoding and one-hot encoding. I'm initializing label encoder function and I'm storing to an object. It is label encoder. Label encoder becomes an variable to store the label encoder object, the function. Now, I'll use label encoder, the object, to fit on the data drivetrain, and the results will be stored back to drivetrain underscore enc. The results will be stored back to label underscore drivetrain underscore enc encoding. Done. Let me open df. So these are my results of label encoding. How many columns did you see in the output? Only one column, not like one hot encoding. It is not like one hot encoding. Okay. In one hot encoding, you will get n categories. If you have n columns will be returned. But in label encoding, even though if you have n columns, n categories, you will get only one column as output. That makes the difference. Okay. Now, I'll perform the same on type column. I'll perform the same on type column. I'll get the same. Yes. So this is how we perform encoding to convert non-numeric data to numeric data. What is the purpose of encoding? Dummy variables is, if there are any non-numeric columns and if you want to convert them into numeric columns, we have to go with dummy variables, dummy columns. Clear? Right. Let us move to the next step in the sequence. It is handling missing values. If there are any missing values in the data, we are supposed to handle it. Okay. What if you don't handle these missing values? They are going to impact negatively on the performance of your model. They'll be impacting negatively on the performance of the model. So that is why we actually, handle missing values. So let me import the required packages. I'm importing NumPy for basic mathematical calculations and pandas for data manipulation. And I'm reading the data from the Excel file. As usual, I'm reading the same data from Excel file using read underscore Excel function and storing the data in df object. Done. I'm storing the data in df object df. Info function will return the complete information about the data set. So df.info will return the information about the data set. I can clearly understand that there are null values. See, in some of the columns, I found that there are null values. In fact, there should be 428 non-null for each and every column. But in some of the columns, there are null values. Now, let us use a logic because we are supposed to handle these null values. We are supposed to handle the missing values. Right? Yes. I'm using a logic to identify the number of missing values that we have under each and every column. What is that logic? df dot is a function which returns true or false, which checks for the values in each and every cell. Clear? So dot sum will actually sum up all these Boolean values and it will return the count of missing values in each and every column. See, under each and every column, you will identify the missing values count, drivetrain, MSRP, MPG city, then weight, so on. So in these columns, I have missing values. We have a function called simple imputer. We have a function called simple imputer, and this simple imputer help us to perform imputation. It helps us to perform imputation. And this simple imputer comes from sklearn package. From sklearn.impute, I'm importing simple imputer. Done. Simple imputer got imported. Yes. Now, under the simple imputer, in order to impute with the values, we should have some strategy defined. Okay. That strategy, there are multiple strategies to impute the missing values. Strategies like mean, median, mode, then constant, random. So there are multiple strategies, guys. Right. So I'm initializing simple imputer. First of all, simple imputer of the missing values. If they're identified as the missing values, the strategy that should be used is mean. So that means the mean of the value will be calculated. The mean of that particular column will be calculated. Once after calculating the mean of that particular column, that mean value will be used for imputation. So let me initialize simple imputer. Done. With the strategy mean, I have initialized mean imputer. I'll use this simple imputer which got initialized and I'll fit it on the data in which we have the missing values. In the column which we have missing values, I'll be using simple imputer with strategy mean and I'll fit it on the data. I'll get the transformed results. Once after getting the transformed results, where am I storing them? Within the same column. So this will complete the imputation. And if you check the results post imputation, if you are trying to get the number of missing values within the column, it should be 0. Should be 0. That means imputation was done. But what kind of imputation did we do? We have performed mean imputation, guys. What does mean imputation means? The mean of the column will be calculated. Wherever we have missing values, that mean value will be used for imputation. That is what mean imputation means. Next to mean imputation, we also have median imputation. The process is same, but what you will be changing is median. The strategy is what you are changing. Instead of mean, let us keep it as median. Let us keep it as median. So now the median value will be used for imputation. I'll initialize imputation. I'll initialize this median imputer. The simple imputer got initialized and that imputer will be used for performing the imputation. Okay, see what's happening. Where did I store the results? I have stored the results in the same column, MSRP, manufacturer suggested retail price. So this will return me, this will complete the, this will complete the imputation. This will complete the imputation, and post completing the imputation, let me also cross check the results. So when I say df of the particular column is any function followed by some function, It should return me 0 as output. Yes, I see 0. That means median imputation was done. Median imputation was done. Next to median imputation, we have mode imputation, guys. What exactly we do under mode imputation? Simple. The mode value will be used for imputing the values. Wherever there are missing values, the most repeated value within the column will be identified, and that column value, that mode value will be used for imputing the data. Okay. So what I'll do is I'll change the strategy. For mode, it is given as most underscore frequent. It is given as most underscore frequent. Okay. So what I'm going to do is I'll initialize simple imputer with mode strategy, and I'll use it to fit on the data. Which column it is? Drive train. I'm going to use it on drive train. I'll fit it on the drive train. I'll get the transformed results. These transformed results will be stored back to, the drive train column. To the same column, we are going to get the results stored. Let me execute the line. Done. Then I'll go and use the same logic is null dot sum, which has to return as 0 because the imputation was already done, right? So this will return as 0. This will return as 0. Clear? Now, next to mode imputation, there is also one more method of imputation. It is called constant imputation. Okay. So when you want to perform constant imputation, you should also come up with a constant value. See, if you don't want to go with say mean, median, and mode imputation, okay, and if you want to use any constant value, to perform your imputation, then you can define that constant value. See, what is my constant value that I'm specifying here? 3500. So this 3500 will be used as constant, and wherever there are missing values, the 3500 value gets imputed. This value gets imputed. And the strategy should be constant. So this will actually initialize. The simple imputer with constant imputation, and I'll use it. I'll fit it on my column weight. I'll get the transformed results. Post getting the transformed results, I'll get these results stored to the same column, and on this column post transformation. Okay. Let me go and check the results, cross check the results. So when I say is null dot sum, it should return me 0 as output. So that means constant imputation was also done, guys. We are done with mean, median, and mode as well as constant imputations. All these imputations we are done. Now finally, let me cross check the results together. I'll go with the info function. This info function will return me, the complete information about the data set. Okay. So when I say info function, it will return me the column names followed by their non-null count. Do you observe any column with null values? No. Done. We are done. So in this way, we are able to perform imputation, which is actually nothing but we are handling the missing values. Wherever there are missing values, we'll identify which strategy should be used. When should mean strategy be used? When there are no outliers. Because if we have outliers, we know that mean gets influenced. And because of it, we cannot go with the mean imputation. If there are outliers in the column, we go with median imputation. What if we don't have outliers? Obviously, you can go with mean imputation. If you are working on a non-numeric column, you can go with the mode imputation, most frequent. Or if you have any specific requirement, only this particular value should be imputed, then go with constant imputation. In this way, you can come up with the constant, the imputation strategy. You can decide the strategy for imputing the values, the missing values. I hope it is clear. So the next technique, the next step within the data cleaning steps is transformations. It is transformations. What exactly transformation does is transformation help us to, convert any data from non-normal to normal data. If the data is non-normal, and if you want to convert this data to normally distributed data, Z data, then we apply transformations. We know that there is a plot called QQ plot, which help us to understand whether the data is normally distributed or not. So here we use the concept of QQ plot, guys. So I'm importing pandas for data manipulation, NumPy as NP for basic mathematical calculations, array handling, SciPy.stats. SciPy is an advanced package for, mathematical calculations, advanced calculations. And PyLab for visualization again, as well as Seaborn and Matplotlib are also visualizations. I'm reading the same data that is present in the CARS Excel sheet. Okay. So read underscore Excel function will be used to read the data. Yes. So I'll be using read underscore Excel function to read the data. Done. Where am I storing the results? I'm storing to a variable, it is df. I'm storing the results to df. Now, let us visualize QQ plot first of all. Because only if I visualize QQ plot, I'll come to know whether the data is normally distributed or not. If it is normally distributed, I can proceed. If it is not normally distributed, I have to apply transformations, guys. What does this transformations does? They help us to, convert the non-normal data to normal distributed data. So the function propplot help us to convert, it help us to return the QQ plot. See what happens. This will return me the QQ plot. And if you observe here, I see the majority of the points are not passing through this red line. So that means under MSRP, the values are not normally distributed. MSRP is not normally distributed. Okay, let me check for weight. Yep. Compared to MSRP, yes, majority of the values are falling, but still, it's better if we apply transformation. We can get the results very best. Why should we work only on the normally distributed data is majority of the algorithms will work well on the normally distributed data, guys. They work well on normally distributed data. That is why, we perform transformations. We perform transformations. Right. What am I doing next to it? I'm performing transformation. You know what transformation I'm using here? I'm using np.square. Square transformation is what I'm using here. I'm using square transformation. Okay. And I'm visualizing this QQ plot. See what happens. Still the results are seen. So the square of the values will be taken to visualize this QQ plot. Still the visualization is not up to the mark. Let me use square transformation on the weight column. Even here, better, but still the same. I don't see the majority of the values falling through the pipe. Okay. Let me use log transformation. The log of the values will be calculated. np dot log of df dot msrp. So on msrp column, the log of the values will be calculated, and that values will be used for visualizing QQ plot. Now you see, yes, majority of the points are falling across this red line. So that is how transformations help us to, convert non-normal data to normally distributed data. Okay. Next to it, what do you have? What do you have? We are going to perform log transformation on weight column. Let's see how the results will be. Here the results are good. Yes. I see majority. Only a few, but majority of falling across the line. They are on the line. So this is called transformations. And under transformations, there are multiple techniques. We have log transformation, exponential transformation, okay, square transformation, cube transformation, square root, cube root, reciprocal. So there are n number of transformation techniques, guys. There are n number of transformation techniques that can be used. Okay, one of the automated transformation technique is Box-Cox transformation. What does this Box-Cox transformation does is, it tries with the different values for the lambda. But the challenge with Box-Cox transformation is, it works only good for the columns which contains positive values. What if the column contains negative values? If there are negative values in the column, Box-Cox does not perform well. The results of Box-Cox will not be good. But Box-Cox works well for positive data. Okay, so I'll use stats scipy.stats dot boxcox. And on which column I'm using? df dot msrp. On msrp column, I'm going to use Box-Cox transformation. Okay, where it returns me the fitted data, the transformed data, and the fitted lambda. So it tries different combinations and it returns the best fitted data and the lambda. So this is the lambda value, the best fitted lambda value, okay, for this data. And let me also visualize the Box-Cox, how Box-Cox helped us to perform the transformation, how the values got transformed. You'll understand now. See, this is an visualization code, guys. Okay, I'll execute all of these lines together, then I'll explain. Yes. You see here in the results, in the plots pane. So this is the original data of MSRP, and post applying Box-Cox transformation, this is how the values got changed within MSRP. Okay, so that is what we are trying to understand. Now let me go back to the code. So I would like to get subplots within one plot of size 10 by 5, in which I would like to get two subplots, 1 and 2. Okay, so in the first subplot, I will get the hist plot. This is called hist plot. Okay, and on which column? On df.msrp. KDE represents kernel density estimation. So you see that line? It is called KDE plot. And in which color? Red color. So it should sit at this position. Axis 0 means this position. And the title for this should be kept as MSRP of original. So on the original data, this is how we are having the hist plot. On the fitted data, how did we get the fitted data? Using Box-Cox transformation. Okay, so in the second subplot, you'll have the Box-Cox transformed results. Okay, the Box-Cox transformed results. And you'll see a histoplot which is normally distributed. Is this normally distributed? No. This is not at all normally distributed, guys. This is not normal. How can you tell that? If you observe properly, I see the long tail towards right hand side, positive how? So it is positive skewed data. This positive skewed data converted to, normally distributed data. How? Transformations. Transformations has given us this output. And finally, print of the lambda values I'm going to get. So this is the lambda value at which we got the best results. That's it. So the purpose of transformations, I hope you guys are clear. What is the purpose of transformations? To convert non-normal data to normally distributed data. And the final step under data cleansing is feature scaling or feature shrinking. It is feature scaling or feature shrinking. So let me clear the memory. Right. So what is the purpose of feature scaling? Why should I scale the features? What are features? Features are nothing but columns, guys. Okay. So the data that we have within the features, the data that we have within the columns, should it be scaled? Yes, it has to be scaled. If you don't scale the values within these features, if you take the raw data directly and if you build a model on the raw data, the results will not be good. Why? We can have a column with very big numbers. Yes, if you see in our case, there is a column like MSRP. There is a column like MSRP. What does MSRP means? Manufacturer suggested retail price. So the price will be very high in number. But there is also a column called engine size. If I compare the values between engine size and MSRP columns, what is happening? MSRP column has very big values compared to engine size. Under engine size, I see only the values which are in single digit. But in MSRP, the values are in 5 digit. So when you try to use such kind of columns, okay, when you try to use the columns as it is, what happens is the model gets biased. The model gets biased towards one such big value column. So the model does not learn. Okay. For that reason, we scale the features. We are shrinking the features. Okay. I'm importing pandas as PD. I'm importing pandas as PD for data manipulation. Then I'll read the data. I'll read the data which is present in an Excel file. Okay. And I'll store it in a variable. It is data. So if you see here the same data, there is no change. Now I'll use describe function. What does describe function does? Describe function will return the descriptive statistics. It will return mean, standard deviation, count, minimum value, maximum value, Q1, Q2 and Q3 values of all numeric columns. And the results of describe I'm storing to a variable. It is DES. So let me open DES. You will find the results for only numeric columns. See, for all the numeric columns, these are the results. Okay, so I can clearly see that there are no missing values. Yes. And these are my mean values, standard deviation, minimum values and maximum value. But I can clearly understand the data is not scaled. How? If you see MSRP, the minimum value is 102.80 and the maximum value is 192.465. But if I take engine size, the values are 1.3, 8.3. So if I take this data as it is and build a model, what happens, the model gets biased towards a column which has very big in number. So if it just depends only on one such column, it should not be trained in that fashion. No. For that reason, we have to go with feature scaling techniques. And the feature scaling techniques that we have are standardization, normalization, robust scaling. I repeat, standardization, normalization, and robust scaling. Before performing feature scaling, I am going to access only a selected columns. For that reason, I'll use an attribute called ILOC. ILOC and LOC are two attributes which help us to access data from a data frame. What is data? Data is a data frame. And I don't want to work on all the columns. I just want to work only on the numeric columns. So I'll use ILOC in which I'll have to pass two values. One is for rows and the second one is for columns. Column represents all rows. Columns represents all rows. But 5 column represents, to access columns from index 5. To access columns from index 5. So that means, let me open this variable data. Index 0, index 1, index 2, index 3, index 4, index 5. What is index 5? MSRP. So that means from index 5, we are going to get the columns. Clear? Yes. So let me get the subset of the data. Now I'll start standardization. What exactly standardization does is, standardization, is a method of feature scaling which uses the formula, it is x minus mu by sigma. It uses x minus mu by sigma as the formula, where x takes the values. Mu takes mean value, sigma takes the standard deviation for that particular column. Okay, and the output of standardization will be, for all the columns, it will return the values as 0. The mean value will be returned as 0. And the standard deviation value, it will be returned as 1. So that will be the output of standardization. In short, when I use standardization, the output for each and every column, even though if it is non-normally distributed, it converts to normally distributed data. That is the purpose of standardization, guys. I'm importing standard scalar. To perform standardization, I'm importing standard scalar. This is from sklearn.preprocessing. Sklearn is a package. From preprocessing module, I'm importing standard scalar. Done. Next to importing standard scalar, I'm initializing standard scalar function. I'm initializing it. Done. Now I'll use the standard scalar function. I'll fit it on the data. I'll get the transformed results. These transformed results will be stored back to df underscore std. df underscore std. What am I doing? And I can clearly see df underscore std is an array object. It is not data frame. I'll convert it back to data frame. So when I convert it back to data frame, I'll get the results stored back to a data frame. Yes. Where are we storing the results? Dataset underscore std. So it is a data frame. How many rows? 428 rows and 9 columns. Done. But there are no column names. For this data frame, there are no column names. That is because of I have converted it from an array. So let us pass the column names for these columns, the output. So what I'll do is, I'll just pass all the columns manually. See, I'm taking list of column names and I'll passing it to the columns of the output. Done. Now if you open and check, you will find the column names. You'll find the column names. Now, I'll finally concatenate the results of standard scalar and the original data, because in the original data we have the non-numeric columns as well. Right? So I'm taking the non-numeric columns and the standard scalar output and I'll combine the results together where I'll get the final data set. So this is my cleaned data using standard scalar. Let me open the data set, guys. If you see here, earlier the values are very big. Now if you see, all the values got scaled. Yes, they get scaled. They get scaled. And if you perform describe on the transformed results, the scaled results on this final data set, okay, let us understand. This is very important. I'll open this variable res underscore std. So if you observe properly, the result of standard scalar, what is, if you see here, the mean for all the columns will be 0. It will be 0. No, I see some values, right? How come it is 0? No, 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 no. It is nothing but minus 1.7 into 10 raised to the power minus 16, which is equals to minus 1.7 divided by 10 power 16. So, which is nothing but obviously 0. It will be minus 0.0000 so on 1.7. So if you go in this fashion for all the columns, you will find the values for the mean as 0. And what about standard deviation? Standard deviation for all the columns will be 1. So I can understand that when I apply standard scalar, when I apply standardization, the output for all the columns, mean will be 0, standard deviation will be 1. So what does this mean? This means your data is being converted to normally distributed data, guys. Your data is being converted to normally distributed data. Only Z distribution will have such kind of properties. What is Z? Z is nothing but normally distributed data. Okay, so that is the purpose of standardization as part of feature scaling. Let us go to the next technique. It is normalization. There is one more technique called normalization, okay, which uses the formula as x minus minimum by maximum minus minimum value. When I use normalization, what happens is all the values get scaled to a range of 0 and 1. It gets scaled to 0 and 1. All the values, whatever might be the numeric column, all the values will be scaled to 0 and 1. What is the formula that it is using? X minus minimum by max minus minimum, nothing but range. Maximum minus minimum is nothing but range. So when you use this formula, your results will be scaled to 0 and 1. So let us also understand normalization by taking the same data set. So in order to perform normalization, we have min-max scalar. The function is min-max scalar. I'm importing from sklearn.preprocessing. Then I'm initializing min-max scalar. The same steps. There it is standard scalar. Here it is min-max scalar. Then I'll use this min-max scalar which got initialized. I'll fit it on the data. Okay. And I'll get the transformed results. These transformed results I'm storing back to a variable df underscore norm. Now, I know that the min-max scalar will return as an array. It will return as an array again. So I'll convert this array back to data frame. I'm going to convert this array back to data frame. So I'm storing the data frame to dataset underscore norm. So this is the output of min-max scalar. And since we have converted it from an array, we'll not have the column names. We are supposed to assign the columns one by one. So I'm just passing the list of columns, all the columns. Yes, done. Now, if you observe properly, you will find all the values between 0 and 1. No value in the entire data set will be less than 0 and no value will be greater than 1. You can observe any value, guys. That is the output of, normalization. Here we are doing, exactly feature scaling. The feature scaling is done exactly here. I'll do the same. I'll perform the concatenation. I'll concatenate with the non-numeric columns. And on this final data set, I'll perform describe. When I perform describe function, I'll get the descriptive statistics on the scale data. And where am I storing the results? I'm storing the results to an object, res underscore norm. Okay. So this res underscore norm, let me open it. So if you observe here properly, what is the output of normalization? The minimum for all the columns will be 0. Is it 0? Yes, it is. The maximum for all the columns is 1. So I can clearly understand feature scaling has been done. Feature scaling has been done. What is the formula that normalization uses? X minus minimum by maximum minus minimum. And finally, the last technique of feature scaling, it is robust scaling. It is robust scaling. When is robust scaling used? When we have outliers in the data. When there are outliers in the data, we go with robust scaling, guys. And robust scaling uses the formula x minus median by IQR. X minus median by IQR. So what exactly this formula talks about is x minus median. We know that median is not influenced by outliers. Median does not get influenced by outliers. So that is why we are including in the formula of robust scaling. By IQR gets calculated for the data. What is IQR? Interquartile range. The middle 50% of the portion of the data. So when I use this formula, when I perform robust scaling, the output for robust scaling will be, for all the columns, the median value will be 0, IQR will be 1. IQR will be 1. So let us apply robust scaling on the data set and proceed. So I'm importing robust scalar from sklearn. Done. I'm initializing robust scalar. The robust scalar that we have initialized, I'll be fitting on the data and I'll get the transformed results. These transformed results, I'll be saving back to an object. It is df underscore robust. df underscore robust. What is df underscore robust? df underscore robust is an array. It's an array object that we got as output. This output I'll be converting back to data frame using pd.dataframe function. So when I use pd.dataframe, the results will be converted to a data frame. So dataset underscore robust is a data frame. But we know that we'll not have the column names. So let me pass the columns to this data frame. When I pass these columns, I'll get the column names. Done. And I'll finally concatenate the results. When I finally concatenate these results, I'll get the final output, the final data set. And on the final data set, I'm performing describe function, guys. And when I perform describe function on the final data set, I'll get the descriptive statistics on the results of res underscore robust. Res underscore robust is what I'm going to use for storing the results. So let us interpret the results of robust scaling. What should be the output? Median should be 0 for all the columns. Do we have median here in this table? Descriptive statistics. Yes. 50th percent is nothing but median. You see, all of them are 0. All of them are 0. But what about IQR? Can I calculate IQR from this table? Yes. IQR is nothing but Q3 minus Q1. Q3 minus Q1. So 0.61 minus of minus 0.38. So when you add, you'll get approx 1. You'll get approx 1. For all the columns, if you do the same, see, if I take cylinders, 0 minus of minus 1, it is nothing but 0 plus 1, which will be 1. So in that way, I can confirm that robust scaling was applied. We have scaled using robust scalar. But when is robust scalar used? In case of outliers. When we have outliers in the data, and if you don't want to remove these outliers, if you find that the outliers are genuine, then we'll not use standard scalar or min-max scalar. We'll use robust scalar, which is robust to outliers. So this marks the end of data cleansing, data pre-processing, or data organizing. And I hope we had a very great session today. So it's time for questions. Any questions? And guys, if you find that the session went well, hit on the like button. Do share across your connections. Any technical questions? Even non-technical questions will be, addressed. Right. If no questions, we'll wind up the meet here. We'll wind up the session. But before that, I hope the concepts of Python, exploratory data analysis, data cleansing are very clear. Right? Thank you. Thank you so much for your feedback. So in order to get the data sets, these data sets are readily available in Kaggle. Okay. These are open source. You can get these data sets from Kaggle. And you need not apply the techniques only on this specific data set, guys. If my suggestion would be, you can download any of the data set which is open source and try applying these steps. Okay, if you find cars data set, that is fine. If you don't find cars data set, you can use any other data set and apply the steps. When you do hands-on, only then you'll memorize the concepts. So my suggestion would be, do hands-on. Hands-on is must and should. Right. Any other questions? Thank you so much for your feedback. Yeah. So utilize this specific time for your doubts, guys. If you have any kind of doubts, yes, we can take it over. We'll be addressing your questions. And from tomorrow, we are going to start important algorithms under machine learning and deep learning. Okay. So each and every algorithm that we are going to cover in the next couple of days, we'll be understanding the theoretical part. Then we'll be implementing on a data set. So that is how we are going to understand each and every algorithm. Yep. Yep. The feedback link has been provided. Please give your valuable feedback before you leave. Thank you so much, guys, for joining and making the session interactive.